I think it's fine to start with the thanks. So I want to thank the organizers for the invitation. It is a pleasure to see so many new and old faces, and we have an interest, a genuine interest in the kind of stuff we do with homotopy theory. So the organizers invited me to give a talk about homotopy theory. So naturally, I'm going to give a talk that's mostly in number theory. So I want to discuss the rationalization of the K and local category. And this title is a clever allusion to a recent paper that discusses the rationalization of the K and local scheme. So hopefully, I will have introduced the concepts involved in both titles. What is the overarching technique that we adopt from this work, and what is our contribution? And by our, I mean myself and Schlank. And this one is actually included. So the main theme that goes into this work and also this work is a novel way of accessing stuff in stable homotopy theory using the machinery of p-adic geometry. In particular, celebrated result written due to faultings and elaborated on and expounded by Scholze and Weinstein, and also Farg, the isomorphism of the towers. So that is a rather heavy-duty number theory result, but I want to preface all of this by explaining what do all of these things have to do with homotopy theory, and what is in fact the kind of homotopy theory we're trying to understand. So since we do homotopy theory, we probably want to understand the category of spectra. That is a daunting task. We don't even know the endomorphisms of the unit of this category. So we settle for a more modest goal, namely to understand K and local spectra. Now, whether you know what this is or not, you might be relieved to know that I won't be defining this concept. Thank you. The reason being that I would like to approach it from less of a homotopy theoretic perspective and more algebraic geometrically. So for the moment, I would like to think of this category as a bit of a black box and approach it by means of descent. So what does that mean? I'll give you a construction. The construction is as follows. It's called. It goes from the a priori category of formal groups of height exactly n, defined over FP bar, going to commutative algebras in this mysterious category. And this construction is called Moravec theory. It sends gamma to E of gamma. Now, you might wonder what this category is. Well, it's kind of simple. There is only one object up to isomorphism, but it has a rather complicated automorphism. So this is just, so in essence, we can pick one gamma, call its image En, and regard it as an object equipped with the action of the automorphism, which is denoted by Gn. And why am I introducing these guys? Well, they have surprisingly robust bearing on the entire category. Namely, the following property holds. If X is any K local spectrum, I can ponder the following construction. I can send X, I can tensor X with En. This gadget has an induced action by Gn, and I can consider the fixed points. A word of caution is warranted. Gn is a profinite group, and I want to consider those fixed points in some kind of continuous sense. At any rate, this receives a map from X, and this map is always an isomorphism. So let's think about what this means. If X were the unit of this category, this just means that the fixed points of En are the unit of the category. But it means something stronger. For example, a fact that is true is that En tensor En, once Kn localized, this should also be Kn localized, is just the functions from Gn to En. So you see that geometrically, this tells us something about En being a Galois extension of the units. Now, there is a slightly more highbrow way of interpreting this fact. Namely, if I look at Kn local spectra, they arise as the following construction. I can consider En modules inside Kn local spectra and do the fixed points at the categorical level. And this is inequality. Now, you're still entitled to be displeased with me because I told you I wasn't going to define Kn local spectra, rather obtain them in some different way. And here I am defining them using themselves. But there is a solution, namely, if I don't care about the entire Kn local category, but only about some subset of it, then I can try to consider the following thing. Instead of all, this is kind of a completeness condition for an En module to be Kn local. So if I consider only those En modules which are perfect complexes, this expression makes no mention of the Kn local category, and it coincides with the full subcategory of Kn local spectra, which are dualizable. So if I'm only interested in understanding dualizable Kn local spectra, then there is a purely algebraic geometric way of defining those once I understand what En is. So maybe I should say a few words about that.
Can you take on the perf of En?
Perf of En is the full subcategory of En modules in spectra, or in Kn local spectra. It's going to be the same full subcategory, which are perfect. That's kind of a special, that's a property of En, that perfect modules viewed as Kn local spectra and viewed as spectra coincide.
Is this just the compact objects?
It's the compact object, and the dualizable object, and the ones thickly generated from the unit. They all coincide. So, at any rate, I have this thing, and I should probably now say something about En.
So
Yes.
you need to know En together with the.
Absolutely, absolutely. So I will tell you everything about En, but the rub is going to be that understanding the Gn action is kind of difficult. So I know what is pi 0 of En. This is, well, it's non-canonically isomorphic to this, the Witt vectors of Fp bar adjoin U1 to Un minus 1, formal variables. And if you know your number theory, you'll probably recognize this ring as the universal home for a deformation of gamma. So this is the Lubin-Tate ring of gamma. And well, the odd homotopy groups vanish, and pi 2I of En is omega to the tensor pi minus I, so like Li of G, D of gamma to this tensor. Okay, so it's an invertible pi 0 object. And as Vladimir was indicating, the action of Gn on this thing, on the homotopy groups, is kind of difficult to access. There are ways to access it in kind of a piecemeal fashion, but it's very difficult to understand it globally. In particular, you will see that it acts kind of strangely on pi naught if you try to evaluate it. And on the higher homotopy groups, it's in a way even worse. There's not a single invariant element. So if one wants to actually understand things that involve En with its Gn action, one has to find a clever way to approach En as a Gn equivariant object. But before I embark on that, let me make a small simplification. Instead of considering this category, which involves something kind of intimidating as in commutative algebra and spectra, I could instead consider this construction. I could consider perf of pi star of En with its Gn fixed points. Now, I should stress that these two objects are unrelated. There is no map between them. But here is the fact, let me call it a proposition, which might appear in the literature, but we actually provide a proof for this. I think you go by B, right?
I usually write BM, but
BM. So the equivariant objects, En with the Gn action and pi star of En with the Gn action become equivalent after tensoring with Q. So not only do we get a map, we get a canonical map and its equivalence and Gn equivariant. So this tells me that if for some reason I care about rationalizing a category, I need to explain two things. One thing is why the rationalization goes past the fixed points. So I claim that in fact, if I wish to rationalize this category, which roughly speaking means to invert P on mapping spaces, this amounts to doing perf of En tensor Q fixed points. And this is one and the same as perf of pi star of En tensor Q fixed points. So this raises the question of how to approach this kind of thing. Namely, how to understand, but we have reduced basically from understanding En with the Gn action to understanding the homotopy groups with their Gn action. But as I was saying, this remains a daunting task. Let's start by understanding pi naught of En.
so pi star then just as a graded ring.
The gemification.
What?
I make it into a ring. I do the generalized Eilenberg-MacLane spectrum.
Can I ask, so
Yes.
why it's tensor Q and not like QP or something? I mean, are we already working P local?
This is P complete.
Okay,
And when I invert P, I invert P. Well, pi naught of En, as we said, has a modular interpretation. You can consider its formal spectrum with its Gn action. This has a name. It's called the Lubin-Tate formal scheme with a Gn action. And you might wonder, is there you should wonder, is there a general procedure for constructing formal schemes with interesting group actions? It turns out that the Lubin-Tate formal scheme is a part of a large family of moduli problems known as Rappaport Sink spaces. So the idea is this. Given some linear algebraic data, one produces a moduli problem which is representable by a formal scheme together with a group action. And this group and the modular problem are all dictated by this linear algebraic data. And indeed, the looping Tate formal scheme with its Gn action is an instance of this more general paradigm. But one can wonder, can I come up with linear algebraic data for which the group action is more transparent? I remind you, the issue is the looping Tate formal scheme itself is kind of simple, but the group action is kind of difficult. Well, these things admit a duality, which I won't expound on, but quite interestingly, it sends the pair looping Tate and Gn to something called H GLNZ. This H is a little complicated, but roughly speaking, it lives inside projective space. And if you believe this description, then the GLN action is just a restriction of its natural action on projective space. So the action is very simple. The scheme itself is quite a bit more complicated, but the action is much simpler. So if I could only tie this pair with this pair, I'd be in good shape. I'd be able to make computational inferences from stuff I know about this to stuff about this.
This duality is for every representing spaces, or just this for specific linear
It's
algebra?
the level of linear algebra
The
there.
duality, yes.
Like, is it like a general property of representing spaces that there's always this duality?
Representing spaces eat up something in linear algebra, representation theory rather, and give you something. There's a duality on the source.
Sure.
Now, it would be nice if I could say something like this. Maybe I could say that the looping Tate scheme modulo Gn in some sense is the same as H mod Gn. If it were so, I'd be in amazing shape, because the category I'm after is at least morally the same as quasi-code of this. So if I could understand, if I would have this equality, I'd be in amazing shape. But that's just false. This type of equality becomes true once I forget some information about the moduli. So there are a few ways to present this forgetting of information that I need. Here's the one I like, I favor. So if X,
The dual there means dualizable object.
yeah, it's
not
the
duality.
full subcategory and dualizable. So if somebody gives me a pre-stack, so a map from some kind of commutative rings, you say spaces, I can forget what it does on all rings but the perfectoid one, which are a full subcategory of commutative rings. And this composition I call the diamond stack of X. And this equality becomes true only at the level of diamond stacks. So whether I want it or not, the theory of representing spaces compels me to think about the diamond stacks of these objects. So this raises the question. I have, on the one hand, quasi-coherent sheaves on LT GN fixed points. On the one hand, I need to consider something much more complicated. I need to consider some category of sheaves associated to this kind of funny modular problem. So I need to consider quasi-coherent, well, sheaves on LT diamond GN fixed points. And I need to consider this, well, there is a map called nu lower star. And I want to understand how much information is lost by applying this map. Why? Because this is the same as sheaves on this diamond stack with its GLN action. Well, that's a bit of a delicate question. First of all, note that I need to take modules over whatever the image of new lower star is. This goes by the name of O plus. And same here. And then it's still not fully faithful. It's not much of anything. Let's try to understand why is it not much of anything. Let's consider X just be the spoof of ZP. Then what is the diamond stack associated to X? The diamond stack associated to X is doing, in a sense, spoof of the ring of integers in an algebraic closure of ZP, mod out by the Galois action. And this is kind of complicated. For example, it has non-trivial cohomology of its structure sheaf. It's QP S1 coachings.
Do you think of this diamond stack? Do you somehow can extend that to get the sheaf on series B to synchronize the stack again?
I may, yes. This is to conform with this terminology. So you see that even when I take a very simple object and I do this operation, I quite substantially increase the complexity of the results I'm getting. Fortunately, this kind of thing is the main complication. Namely, for algebraically closed fields, there is nice behavior. Let me state this as a theorem. So it's a theorem due to the first paper I cited, so BSSW. If X is nice, defined over C, well, if X is nice, then I can compare the global sections of the structure sheaf on X S1 cochains with the global sections of the diamond stack. That's not quite an isomorphism, but crucially, the cofiber is bounded P torsion. So you see that the passage to the diamond stack only affects torsion information. And this is very good for us because it allows us to prove the following theorem. So the functor. So we have K in local spectra dual P inverted, which is the same as quasi-co on LT. Well, let's call it spoof pi star of GN action, GN fixed points. Rationalized, I can almost say that it fully faithfully embeds into O plus modules on sheaves on LT diamond GN fixed points and P inverted, except I need to account for the fact that there is this added S1 coaching thing. So you can just formally manipulate the source to account for this additional copy that you're getting. which is an operation we denote by brackets epsilon. So the upshot is that this composition is fully faithful. Now, why is this useful? Why are we bothering with this? So the language of diamond stacks tells us this is the same as mod O plus sheaves on H, this GLNZP, P inverted. You can wonder, does the fact that I got a fully faithful embedding into this does it help? Well, the answer is it does. So the original application concerns the following question. We can consider the structure sheaf here, the unit. So it's the K local sphere adjoin this epsilon. And it goes here to something. So it goes to the structure sheaf, O plus. And I can compare the anthropomorphism. So I got this, R gamma of O plus, GLN fixed points. And I can wonder, is this any more approachable than the thing I started with? I remind you, this is kind of delicate. This involves understanding the GN action on the looping Tate ring and more. This is strikingly simple. This is just R gamma of O plus. This turns out to be, well, up to torsion the same as ZP S1 cochains. That's a salient feature of the fact that we can understand explicitly the GLN action on the H moduli problem. We can compute those things. And it turns out that this is just doing this thing, GLN fixed points. So from this one deduces, and you see the action is trivial. It's a matter of algebra to compute the fixed points. And from this, there is the following very powerful consequence. So it's a theorem, BSSW, that if you take the K local sphere and rationalize it and do homotopy groups, you're getting an exterior algebra over QP, zeta 1 to zeta n generators, zeta I lives in degree 1 minus 2, which was the long-standing conjectural description of this object. You can wonder, let me close by posing the question, what kind of thing does this extra information bias, does this further categorification bias? And I will posit that this puts us in a position to understand this operation, namely rationalizing a K-local spectrum and then taking homotopy groups for things like cochains on high finite space. So say this. You would like to take this, run it through this functor, understand the sheaf you're getting on this Greenfield upper half space, and somehow understand its global sections with their GLN. Thank you. Yes.